Okay. So in February 2011, a computer program named Watson made history. It beat the two reigning champions of a television program called Jeopardy at their own game. None of us who were in the room that day when they taped the show, we didn't know that it could win or it would win. It was really in the balance. It was a real live experience. But once Watson won, we knew that something fundamental had changed, that we were no longer in the same world we had been in, that in fact, it was the start of a new era of computing. What do I mean by that? Let's look back at the history of computing. Back in the very old days, we had machines that we put together, starting with the abacus, to help us add and subtract and multiply and divide. Then a little while later, in the era that most of us in this room were born into, we had programmable systems. With these systems, they didn't have a fixed set of operations, but instead, you could give them instructions. And as time went on, it became easier and easier to tell them what to do, allowing these computers to take over more and more business processes and do more and more complex tasks for us. They keep playing the little lights here. Okay, so by now, computers run almost everything. Almost everything we do in our daily day, computers are somehow a part of. But we still have to tell the computer what to do. In this next era of computing, where we will be going is into a world in which computers will learn for themselves what to do, or we will teach them as we teach our children. But it will be a very different way of interacting with computers, and we should be able to create much more powerful systems that will really be able to help mankind move forward quickly. So what do I mean by cognitive computing? Well, cognitive, or the word cognition, come from the Greek word kognos, to know, right? It's all about things that happen in the brain, how the mind can be capable of making judgment. So cognitive systems are ones that do the sorts of things that we do, that can, for example, learn, that can find better ways of communicating with people in a much more natural and expressive way than today's computers do, that have their own built-in expertise, just as humans do, or that are not fixed like those early systems, or even have to be told step by step what to do like our programmable systems, but systems that evolve through experience, both their own experiences and through being taught. And another thing about cognitive systems is just as we are capable of taking in huge volumes of data and doing quite complex processing on it, much more complex than you realize, so also these cognitive systems will need to be able to work at an enormous scale, both in terms of computation and in terms of the amount of data that they will work with. Another way to look at cognitive computing is as a theoretical framework, a way of thinking about the programs and the systems that we're creating by analogy to the human. And these cognitive programs will be ones that can, for example, enhance information organization, or can learn and understand, and that will do so to help us, to be our true partners or assistants in the tasks that we want to make happen in the world. Does anybody here know the TV show Star Trek: The Next Generation? Raise your hands, okay. Do you remember Lieutenant Commander Data? He was an android, that is a cognitive system, right? He was a cognitive system embodied in a human shape, right? That worked closely with his partners on the starship to solve problems, explore space, and all the other things that the Star Trek folks did, right? We are a long way today from being able to create Lieutenant Commander Data. He's still science fiction, but in some sense, when we talk about cognitive systems, that's the goal that we're striving for. Something that can really partner with us, that will not have some of our same frailties, but that will work to serve us, and leveraging what a computer can bring, larger memory, never getting tired, all these other sorts of abilities for our benefit and our good. So let me go back to this notion of the human being as a model for a cognitive system. You see on the right here a human being. We see things, we hear things, we feel things, so we have perception. We remember what we have seen and what we learn, some of us better than others. We learn concepts and facts. We have our own kind of logic. We understand rules and how to think and how to reason, and we use that to solve problems. And we can act on the world, right? We use our physical bodies and our voices to change things in the environment, and that's what actuation is about. So also for these cognitive systems. Cognitive systems, they perceive. Some of them will actually use vision as a means of perception, but others will perceive by means of sensors such as radar or sonograms or so on. All these different kinds of devices, temperature gauges, they can go directly into the computer and be ways for the computer to perceive. They will remember things, of course, they're very good at that. They will learn, again, not just facts, but concepts, and they will be able to continue to improve their model of the world. They certainly are good at logic, and they will start to use that logic to reason and to solve problems, as we do. And also, they act upon the world, even today, right? Whether it's just giving you a response to a question, fetching a document that you asked for, or if it's something more elaborate, like a robot reaching out an arm and grabbing something. We have a lot of different ways in which computers today can act on the world, maybe controlling heat sensors in a building to optimize power. And then the other thing that's important with these cognitive systems is, just like us, over time, they will develop a sense of identity, of who they are, of a name for themselves and a relationship of who they are with relation to the world, just like Commander Data, right? And be able to take their places there. So as we think about this model of human cognition and what it can tell us about the machines and the systems that we're building, we need to use that to think about, you know, as where do we go in the future for these cognitive systems? We will have to build and increase their capabilities in all of these dimensions for them to grow their expertise. So I told you about the three phases leading to the cognitive era, but we are somewhere in the middle between the programmable systems era and the cognitive systems era today. How are we going to bridge that gap? Well, my answer will always be data. The Star Trek guys got it right. There was a reason Lieutenant Commander Data was named that. It's because data will be the fuel that will get us from one world view, the programmable systems era, into this cognitive systems era. And it's already starting. As you know, we have lots of data today. Anybody out there know what a zettabyte is? Okay, 21 zeros, 10 to the 21st bytes. It's a lot of bytes. We've tried various ways of conceptualizing it. It's really hard for a person to understand that much data. What we can say is that 1 zettabyte is about what would happen if you took all the information in the United States' biggest library, the Library of Congress, and you replicated that 100 million times. That's 1 zettabyte. A lot of information. Right now in the world, we have 3 zettabytes of information. The analysts, the IDC company, is predicting that there will be 40 zettabytes by 2020. Their prediction doubled in 3 years. So 3 years ago, they thought there would be 20. So things are changing rapidly. A lot of that growth is coming from what are still, if you look at the span of history, new forms of data. All the data that is coming from cell phone users and voice. All the data that is coming from the social media. You guys go home every night and make more data for us. Thank you very much. Actually, you probably do it during the day. So, sensors and devices, the Internet of Things, right? They say that by 2020, there will be 3 times as many devices in the world as there are people connected to the internet. It's amazing, right? Just really hard to understand. And then there's tons of other facts and figures. But this is really great. This is really exciting because data is exactly the fuel that cognitive systems need in order to learn and in order to do more and more sophisticated things. So what I'm going to try and do now is show you a few what I will call baby cognitive examples. And there are many more. I heard about a few today. Some of the master's students are doing some of these that we've been working on, that just to give you a feeling of what we can do with data today and what we're learning from it. So one of those has to do with this whole area about being able to find the root cause of a problem. In this case, an outbreak of a foodborne illness. So it turns out that foodborne illnesses, that's where you eat a food and you get sick, right? 48 million people each year in the United States alone get sick from eating bad food. It's a huge number. And the United States, it's a pretty well run. We have pretty safe systems for food. It's really bad that that many people get sick. That's a bad thing. But another bad consequence of all this is that amount of people getting sick results in about $80 million, $78 million, $80 in economic damage. How so? Well, when somebody eats something that was poisoned, they don't know exactly what caused the problem, right? So you have to figure out what the cause was. Until you figure out what the cause was, typically what happens is people have ideas and rumors fly around and food gets thrown away, right? That wastes a lot. Also, people get sick, they go to the hospital, that costs money. Also, those same people don't go to work, so their jobs, don't get done, so productivity suffers. You add it all up, it's a lot of damage. So what can we do about it? Well, big data to the rescue, right? Imagine you had a cognitive assistant that could understand large volumes of data and could piece together those pieces of data to answer questions like what caused this outbreak of a foodborne illness. And that's exactly what we're showing with these couple of pictures. We did some work with the German government, sort of their Bureau of Public Health, more or less, where they gave us 2 kinds of data. Well, they gave us one, and then they helped us get other data. They told us where incidents of foodborne disease were occurring, and so those are plotted on this map here. And then they also gave us the routes by which food moves from where it was created to where it's eaten. Using those 2 pieces, our system was able to create models that can in fact predict the cause. And what you're seeing on the right is a view of the sort of the dashboard that we put together. This picture is actually a simulation, so it's looking back in time at a very severe outbreak of E. coli borne illness that happened in Europe. These bad E. coli got out. 4,000 people ultimately got sick. Several people died. The outbreak lasted 8 weeks. By the time they figured out what caused the problem, it had all been eaten. So they threw out all the wrong food, and we ate all the bad food. Not a great scenario. What this picture is showing is, on the right, you're seeing the different days of the outbreak and how many cases were reported each day. We've been running the simulation forward, so that blue line shows that we're on the 10th day of the outbreak, and we've had, at this point, 41 cases, only 41 as opposed to 4,000 reported. And what you're seeing in that circle is the computer telling you 97% certain that the problem was sprouts. Guess what the problem was? It was sprouts. They came from one bad farm in one Middle Eastern country. They went throughout Europe. People got sick. So that would be a cool kind of cognitive assistant to have, right? Here's a very different example. Kind of fun. So everybody's very excited by social media data, right? I don't know how many of you are Twitter users, but if you are a Twitter user, you're one of 230 million people who tweet. And amongst you, I'm not one of them. Did you get that? Amongst you, you manage to do about 500 million tweets a day. Okay, fine. So people are analyzing those tweets for all sorts of cool things. We're doing something a little different. We've been talking to psychologists who have known for a long time that if they can get a big enough sample of how you speak and how you write, how you use language, they can run some analyses that kind of project your personality profile, your basic needs, you know, what motivates you, and your values, what do you care about in the world. So it turns out 200 tweets, and we can give you your personality profile, right? This is now out there as Watson user modeling, I think, is the name of the product version of this. But you can go try it. All you have to have is an active Twitter handle and at least 200 tweets, and it will build you a badge like you're seeing up at the top. That's a teenage volunteer. She was very excited. She's less neurotic than her best friend, okay? So, I don't know, teenage girls love to find out about themselves. So, okay, but all joking aside, it seems that this can have actually very interesting business applications, and that if your cognitive agent is in essence your psychologist that's sitting there and analyzing your client set, we can tell you things about how to market to them better, which products they might want to buy, even if that's not a wish that they've expressed yet, or where their fan club is and who's loyal. Or we had one company come in and we kind of gave them the profile of their collective customer set. And then we showed them the profile they asked us about a designer they had just hired. And so he tweets a lot. So we did his profile in real time. This is very fast. And we're able to show that that designer's profile matched very well with their client base. So then they asked us about the one that they almost hired. They really had a hard time deciding. His profile, his personality, totally different from their clients. If they'd hired him, they might have had a disaster because he would have been trying to change their line of clothes in a way that didn't help their clientele. So I think there's some really interesting things that you can do with this. Here you see a plot geographically, and you can't quite read it on the big screen, but In addition to demographic information, we're telling you things about certain personality characteristics like openness to experimentation, how worried are you about taking risks, and other sorts of features like that. And then as a last example, of course, Watson itself was a cognitive big data application. Watson was fueled by a lot of algorithms, new algorithms and old, that were basically brought together in order to learn from a collection of knowledge that came from feeding Watson the moral equivalent of 1 million books, right? The data actually came from hundreds of different web sources. Some of it was very structured, tables and facts and so on. Others was just raw text of various kinds. And so a lot of the innovation, a lot of the technology was just around how do you extract the meaning from the noise of all this data, and how can we put that to work for us. So I've given you some examples now of, see, I cleverly took my watch off. Okay. I've given you some examples of the kinds of things we can do today. And this is the IBM view, but there's many other companies doing similar sorts of projects. What I will say is, what I will focus on next is where do we have to go and where are we going? What are some of the more advanced features we can imagine working on? And these are things we are just working on. They don't work today. But so that we can get to a true partnership with these computers. So in particular, I'm going to talk about two very, very challenging cognitive tasks. One is about complex decision support. We all make complex decisions. A lot of us would like to have somebody smart nearby helping us make those decisions, analyzing the arguments for us, helping ensure that we don't miss something before we make that decision. And the other one is, again, arguably even harder. It's how can you teach the computer to do a very human thing, that is, discover new knowledge. So I'm going to tell you about a couple of projects there, and then I'll talk to you also about a project where we're looking more at the interaction between people and the computers. And if all goes well, there'll be a short movie to kind of demonstrate what I mean there. Okay, so let's start with debate. Now you're scratching your head and saying, why debate? Well, it turns out that when you try to make a complicated decision, you are in essence having a debate with yourself. You have to construct arguments and rationales, you gather facts and evidence. So a lot of what we do in complex decision making looks a lot like what we do in preparing for a debate, at least. Most of the questions that any of us try and deal with in our day-to-day lives are not simple yes or no answers. They're things like you see here. Should IBM make a strategic alliance with Apple? They actually did this chart before we announced our strategic alliance with Apple, so you know what we decided. But, you know, was that a good decision? Well, we'll find out, right? Should I buy a house or rent? I'm only going to be here for a certain amount of time, right? More complex societal questions. And I'll use this as an example throughout. Should I ban the sale of violent video games to children, to minors, to people who are young? So, you know, those are all complex questions. Can a computer help us solve them? Yes, but the existing technologies that we have today, they're just not enough, okay? People immediately say, well, I'd use search. I'd use search. Search will help you find passages that are interesting, that might tell you some good things about the problem. but you would still have to sit down and figure out the arguments pro or con, for or against yourself. Question answering technology really only deals today with yes-no answers. It doesn't know how to construct an argument and weigh the causes. So we need to go beyond that, and that's where what we call our debating technologies comes in. The idea of this research that we're doing jointly with a number of universities around the world is to use the big data that are out there to learn how to construct arguments and then enable the computer to, in essence, be our research assistant when we have to make complex decisions. So let me give you a feeling for this task. In order to do this task, just as if I were going to do it, you have to know what I mean by an argument. What is an argument? We need a model for that. So the way we usually think of arguments, an argument starts with a topic, and just a simple statement that frames the discussion we're going to have. So here, my topic is going to be the sale of violent video games to minors should be outlawed, banned. Then, beneath the topic, usually you have one or more claims that either try to make the case for that topic statement or make the case against it. A claim can be positive or negative, pro or con. And then to support those claims, you need evidence, right? You'd go off and you'd look for facts that would back up that claim. Okay, so that's a pretty simple model. All you have to remember is topic, claims below that, evidence to support the claims. So now I'm going to give you a test. And it's not fair because it's in English, I apologize, but you know, we do what we can and you guys speak beautiful English. So I'm going to pretend that we're having this, that we're doing this argument preparation. And the first step, we have a topic. Now our next step is going to be to find some good claims that would help us, you know, learn and proceed with this argument. So they have to be good claims. And what I'm going to do now is show you a set of statements, and I just want you to yell yes or no, right? Is it a claim or not? Okay? So the first one, violent video games should not be sold to children. Is that a useful claim? No. Well, you're a smart crowd, right? Or you've heard this before. No, because it repeats the topic, okay? How about this one? Violent video games are significantly associated with increased aggressive behavior. Okay, we got a ringer in the front. Okay, yes, that's a factual claim, right? It's claiming to be a fact. Now you'd need evidence to support that it was a fact, right? How about Doom has been blamed for school shooting? I see heads going no, so we'll give you that. No, that's too specific. It doesn't really help support the general argument. Only children predisposed to aggression are affected by violent video games. Yes? No? No. No, because actually that could be used to support both positive and negative. Think about that for a minute, right? If it's only children predisposed to aggression that are affected, why ban it for all children? That's not fair, right? On the other hand, if any children are affected, don't you want to ban it for all of them? So it's an ambivalent statement. It doesn't really help us. Okay, TV shows just mirror the violence that goes on in the real world. Not so sure. It's irrelevant. It doesn't actually address the claim, right? Video game publishers unethically train children in the use of weapons. Mixed reactions in the crowd. Yes is correct. This is an opinion, but it's still a claim, right? It's an opinion, but it is a claim, and it's a useful claim. if you could find more materials that would support it. Video game addiction, I promise this is the last one, you can see we're at the bottom, is excessive or compulsive use that interferes with daily life. Claim or not? Oh, come on. Take a guess. No. That's the definition, right? It's a definition of what video game addiction is. It's not a claim, it's just a definition. So you can see this is a hard problem, right? We're all smart people. We all have at least a college education or getting one. And we have troubles with this. How are we going to teach this to the computer? Well, the basic idea is we'll teach humans. We'll get humans to label a lot of arguments, to find some good arguments, find the claims, find the evidence, and so on for us. And then we'll get the computer to learn. And we'll do that first for claims, then for learning points of evidence, then for understanding whether these evidences or claims are positive or negative, learning how claims relate to each other, because if you're going to construct a really good argument, you want your claims to build on each other in different ways. We're just at the beginning of what's going to be a very long task to start to learn and teach the system. What we think will happen is that eventually it will start to learn well on its own, that is, as it gets enough data and enough experience. But we don't know for sure yet. We've collected an initial set of data using primarily Wikipedia, some newspaper articles. That first version of the data is available for academic research, so if anyone's interested in joining this particular endeavor, there's a paper that will tell you how to get the data and get access to it. It's a very hard problem. It's a very exciting problem. If you could get computers to do this kind of high cognitive task, wouldn't that be cool? Second example, moving on from a hard problem to an arguably very difficult, very, very hard problem, the problem of discovery. And this is some work we're doing with the Baylor College of Medicine today, but I think more universities and more establishments will get involved as we go forward. We're trying to figure out how to discover new truths in medical science. But before I go into that project a little bit, I would like to give you an example of discovery and some of the challenges with discovery. And in particular, I'm going to take you back in history to World War I. Well, actually, we'll start before World War I. So the truth is, discoveries come from all sorts of odd places. And in this story, a very important discovery from medical science came out of having, it came out of what's arguably the worst atrocity that was committed in World War I. What had happened was in the early 1900s in Europe, they were very anxious to find new dyes for textiles to cover them. And so they were experimenting with lots of different chemicals and building up big warehouses of chemicals. Comes the war, they think some of these must make good weapons. And somebody got the brilliant idea of taking mustard gas, which happened to be one of those chemicals, packaging it in bombs marked with yellow crosses, and bombing the Allies in, of course we always make them sound like the good guys, the Allies in Belgium, in the area around Ypres, Belgium. So mustard gas was a very effective weapon. It kills by keeping you from breathing. It hurts your lungs, it burns, it causes blisters, it causes blindness, all sorts of bad things happen, but they didn't really understand why. So 2 years later, some scientists are doing some follow-up research on the people who survived that bombing. And they discover those survivors were needing blood transfusions every single month. And they find out that the reason for that is that the mustard gas is attacking their white blood cells. It's really hurting the white blood cells in the bone marrow, and that the reason the blood needed to be replenished is these people were losing their whole immune system, and so if they didn't have the transfusion every month, they would die. So the doctors, victory, we figured out how this works. They published their paper in some medical journal somewhere, and then they went on to other things. At around the same time, so we're in 1919, some researchers in a totally different part of the world realized that leukemia was being caused by a problem with white blood cells proliferating. You have too many white blood cells, then they crowd out all the red blood cells that carry nutrients and so on around your system, and you also die, right? Your body doesn't get replenished. Your cells don't get the nutrients they need. So in 1919, we knew leukemia was caused by too many white blood cells affecting the bone marrow. We knew that mustard gas attacked white blood cells. 25 years later, somebody made the connection. Oh, well then mustard gas must be able to be used to treat leukemia because it kills white blood cells. And that's what we're looking for, is a way to kill these white blood cells that are out of control. They tested it on some patients, particularly a couple with large lymphomas. The patients survived, they got better. History was made. That was the very first use of chemotherapy in cancer. So it spawned a whole nother way of doing science. But 25 years from when all the facts were known to put 2 and 2 together. Why? Right? Both published papers, different subpools of medicine, right? Lots of literature out there. People can't keep up with all the published papers. Nobody read both papers. Nobody knew, right? In fact, they almost had to go back to first principles to rediscover this. So a very exciting story, but how can we speed that up? And how could a computer assist us? How could a cognitive system help us to actually make this kind of discoveries that perhaps are languishing? Not all discoveries, do you have all the pieces and just don't put 2 and 2 together? But we think there are probably a lot of them. The scientific literature is so large these days that you really can't expect the right people to have read the right articles. So could a cognitive system actually help us with this problem? That's what we're trying to figure out and prove with the Baylor College of Medicine. And again, we're looking at a problem in cancer. Why cancer? Everybody cares, right? It's a very big problem. So I'll teach you a little bit, very little bit of biology, because that's all I know. And then I'll tell you what we've been doing. So the first thing you need to know is that there is a gene called P53 that makes certain proteins that kill your cells, not at a bad time, but at the right time, right? Cells are supposed to have a life cycle just as we are. They're not supposed to live forever. When they start living forever, they keep multiplying and you get some kinds of cancer. It's not all kinds of cancer, but that's one of the big causes for cancer. People have known that for, 30 years, right? A long time. As a result, there are 70,000 articles that have been written about this gene. For the last 20 or so years, we have known that there are other proteins, and it's a class of proteins called a kinase, that can make that darn P53 gene work, right? So if it's not working correctly, they can make it work. The problem is some kinases have a lot more impact than that. They start other processes that maybe you don't want to have going on, right, that could be bad for you. Or maybe they don't quite make it work enough, etc. So there's been a very active search for these kinases. But we've still, despite the fact that a lot of scientists are focusing on this problem, they find about one new kinase every year, okay? And there's way more articles just on kinases and what they do in general. So again, you know, if you're a really, really good researcher, at the end of your day, you go home and maybe you read 2 scientific papers a night, it's going to take you 100 years to read all the papers on just P53. So nobody's done it. Big surprise. What we wanted to know is, could we teach our computer systems, basically building on an advanced version of Watson, could we teach it enough about genetics, about P53, and so on, that it could start to learn and build a model from the literature of how different proteins relate and so on, and eventually be able perhaps to predict what a new kind, what proteins might be kinases and which might not. So that's what we've been doing for the last, well, actually, depends how you look at it. We started a year ago, but 3 months into that work, we had our very preliminary first system running, and that system was already making predictions. And so we said, okay, let's see, are these predictions any good? And so we told the system, you can only see the literature between the beginning of time and 2004. So that's, you can read all of that, but not the last 10 years. You haven't seen the last 10 years. So in essence, we did a retrospective analysis. We said, given the literature up to 2004, please tell us what you think could be new kinases that aren't mentioned in this literature. So those colored, okay, so the green dots on in that diagram, it's a way of plotting the protein families based on a sort of a bag of words model. So proximity means somehow they're more closely related in the literature. So the green dots were the known kinases. I hope you can see the colors. And then the other colored dots are the ones that our system said, hey, these might be kinases. Okay, so then we looked at the literature from 2004 through 2014. Those orange dots, the 7 that are colored in orange, those were discovered in those 10 years to be kinases. So pretty good, huh? The system found 7 legitimate kinases and predicted them, just with some very simple models and analytics. This isn't the only analytic being run. I see somebody trying to count the trees. It's just a good way of showing. Then these others, you know, what about them? Well, just because the literature doesn't say yet that they're kinases doesn't mean they're not kinases, right? So we've started to do lab tests, and that's what's been taking the last 9 months and will continue for some time. But we finished tests on the 2 in red. They are kinases. They had not been discovered before. Our program discovered them. We're really excited about that. That's just like really cool. We don't know. Is this just an accident? It happened once, it'll never happen again. Maybe all these yellow ones are garbage, but maybe not, right? It just takes time to run the biological tests to understand what's true and what's not. Even if our system is, you know, 100% accurate, which we really don't expect, this is a very narrow problem. We actually only fed it the medical abstracts. The model it's building is not very robust or deep for medicine. There's just a lot more that has to be done, that must be done, even in this domain of medicine, to make for stronger predictors, better science. But it's a very exciting tool. You can believe that these researchers at Baylor are thinking, you know, they're hoping for an article in Science, Nature. They're seeing fame, glory, a Nobel Prize. You know, let's not get carried away, but it's really exciting for us. The initial results were published in a computer science paper. We're very careful about what we promise. We just say the lab tests are very promising. But in the KDD, the Data Mining Conference in 2014, it was nominated for a Best Paper Award. So very cool piece of work, very hard problem. Again, a true cognitive task that we're now working to tackle with computers. So the last example I'll give you here is a story about a new way of working with computers that will hopefully help us do decision support and discovery in a way that will be more natural for the human beings involved. And it has to do with creating environments in which the computer, the cognitive agents, or we're calling them cogs these days, and the humans and the devices that both the computer and the human manipulate can all be in the same shared space. So this is a picture of something we call the Cell Lab, or the Cognitive Environment Lab, at the T.J. Watson Research Center in New York. So this is our big mothership research lab. And they're building this environment as a place, again, where all these different elements can come and work together. They want me to be very sure to point out that a room might be just one instantiation of environment. There's no reason in the future that your car wouldn't be a cognitive environment, your house, you know, maybe a restaurant that you go to could be cognitive. Maybe when you go to the theater, it will be a cognitive environment and experience with you. Okay, but what is all this cognitive environment stuff? What does this thing do? Well, the idea is it lets people and the computer interrelate naturally, maybe with natural language, speech, etc., with a lot of different, you can see there's tons of displays there. There are other kinds of very nice visualization tools and devices. We keep experimenting with more. You can see some telepresence robots over in the corner. Because IBM research is very distributed and we work with colleagues all over the world, we've found it's useful to allow them to come and visit us in the labs. And so they do that via these robots. So just different ways in which people can interact to solve some very hard problems. What do we mean by these cognitive agents? Well, really we mean the same kinds of cognitive systems I've been talking about. Some of them will be specialists in particular domains, so maybe a finance cog that knows about smart swaps, or perhaps a cog that understands emergency planning and knows what to do about a critical emergency situation. Others will be sort of more general modules that will know how to do, for example, a certain kind of mathematical analysis, maybe a fact checker or a sensitivity analysis or a sequential Markov decision process thing. You can think of these almost like widgets or apps. It's just cognitive terminology for the same thing, being able to construct sophisticated behaviors by using a general variety of different agents. And the reason we want to do that, of course, is that it's very hard to construct a monolithic system that has all the intelligence that you'd want in the world. So we think maybe having these different agents in this distributed environment, then able to interact naturally with the humans, is going to be a good way to do this. So now I'm going to try and play a little video for you. Give my voice a little rest here. Let me tell you the scenario. You're going to see two of our researchers who are pretending to be in charge of acquisitions for a big company. And they're looking at the next company they want to acquire. And they're interacting in this cognitive environment with an avatar. They're going to call it Watson. We currently call the Cell Labs avatar Celia. She's become a girl, and kind of appropriate to the room. But this is Watson, or at least they'll call it Watson. It does invoke Watson at some points. And they're going to have a dialogue with it. They're going to ask Watson for information. It's going to try and project and do that in natural forms. It's going to try and help them make decisions. And at the very end, but the video cuts out there, it's going to start to make recommendations. And then when they do the demo live, they go on and have the system, the environment explain to them why it's recommending certain kinds of things. So let's see if this works. Otherwise, we'll use my chart. So,
Watson, I need help with acquisitions.
Hello. How can I help you with mergers and acquisitions?
Watson, show me companies with revenue between $25 million and $60 million pertaining to analytics.
Let's see what I can find. I found 87 companies.
Nice.
Okay, so that's a good start. What do you think, Brian?
But I was doing some homework, actually. I think we should pull in that Watson Strategy Group document. There's a lot of key concepts in there. Let's feed it to Watson.
All right. Watson, please regard this as cognitive strategy.
Watson, show me companies with revenue between $15 million and $60 million pertaining to cognitive strategy.
Let's see what I can find.
Yeah, this is nice.
I found 112 companies.
Now we're getting a lot in here. And we can see we're getting some connections to it.
Watson, show me companies that are about analytics and cognitive strategy that are most similar to the companies named Wolfram Alpha and Kawasaki Robotics.
I found 3 companies similar to the ones you specified.
Beautiful.
Well, let's see what we think of these.
Dive a little deeper. Let's compare these things.
Sure. Watson, show me a decision table.
Here is a decision table that will enable you to compare companies side by side.
Watson, place the companies named Wolfram Alpha and Kawasaki Robotics and Cognalytics and Raytheon BBN Technologies and Decisive Analytics in the decision table.
Okay.
Nice.
Okay, but I think we need a little more than that. We need some other attributes. Watson, place the attributes named revenue and employees and corporate structure in the decision table.
Okay.
All right, so now we've got this side-by-side comparison. What do you think?
Yeah, I think that's right.
Watson, give me a suggestion.
I have a suggestion.
okay. So you get the idea. That actually works. It's really kind of cool when you're in the environment and they're talking to this computer and it answers them, and they, you ask a question and they have to repeat it because they have the mics on, but it answers. Very cool stuff. So that's kind of an idea of how in the future, taking advantage of what the human knows about what makes a good acquisition, what are the right features to look like. Okay, that was a baby example. You'll be maybe able to just kind of work with your computer just the same way you're working with your partner to try and get back. Okay, so so far this is also good, very nice. Watson can do cool things. Cognitive computing is headed into the future. It's going to be even cooler and greater. But I think, one point that we have to keep in mind is that in order to run Watson, we need a room full of computers, right? It eats a lot of power and energy. And unfortunately, these complex cognitive systems I'm imagining, they're going to need a lot more. So don't worry, help is on the way. Another group of researchers in our labs have been working with a worldwide team from industry, academia, government labs to try to create low-power chips that work the way our human brains do. Oh, sorry. First, I was supposed to give you an example of how bad this could get. So a brain simulation of 100 trillion synapses and 100 billion neurons, that the brain itself only took 20 watts to perform this task. We ran it at Lawrence Livermore Labs on one of the lowest power supercomputers in the world, right? Took 8 million watts. It required 1.5 million processors, and it ran 1,500 times slower than real life. P.S. if we wanted to do it in real time, 1 second of real-time simulation would consume 12 billion watts. I can power most cities for a few hours on 12 billion watts, okay? It's a lot of energy. So no way can we do the kinds of things that we're imagining with the technologies we have today. So now I'm supposed to tell you help's on the way. We're now trying to build chips that actually mimic the way the human brain works. They have neurons, they have synapses that connect them up. They spark at very low power. They're created with very low power. And hopefully this will help us with our energy problems. We're very excited because in August of this year, our first article on the chip appeared on the cover of Science magazine, which is, you know, it's the holy grail for some of the scientists out there. So very, again, exciting, long way to go. But let me give you some idea of how this works and how it would go. Today's computers, you can think of, you know, they're the von Neumann computers. They have a lot of advantages. Sometimes people say they're the left brain in some sense, right? They make fast decisions. They, in the computer's case, fast calculations. They're fast, they're symbolic, they manipulate symbols. They are precise and accurate. They are very good at, they're programmable, right? They're very good at following orders, and so on. And they eat a lot of power. If that's what today's architectures are like, then these brain-inspired chips, the chip itself is called True North. The systems we embed them in we call synapse. So this synapse system can be thought of as our right side of the brain, right? It's much slower. Every individual neuron is very slow, just like our neurons are very slow compared to what computers can do. But they pack a lot of power when we put them all together, right? They're not symbolic, they're sensory. They're based on input coming in from our sensors. They're not programmable per se, although we do learn and encode over time. What they really are is learning systems. Oh, that sounds cognitive, doesn't it? Right? And they're low power. And so that's kind of the two worlds that we're trying to figure out how best to marry going forward. But first we have to make these synapse systems really real. So this is just a quick picture. On the right you see a single True North chip. And you can see there's a part labeled neurons, so those are the main functional components. Then that's one core of the chip. You put them together in a 64 by 64 array, you have the True North chip. So whenever we talk about True North, it's that array. This kind of shows what they're like in action. What you're seeing is a thermal image. On the left is True North. On the right is an FPGA chip that's feeding data into the True North system. And you can see, you know, it's much cooler than the hot FPGA. And now we're putting them together, of course, into systems because, you know, you've got a 64 by 64 array. Okay, well, you can, you know, connect that together in a very regular form to build bigger and more capable systems. How you get them to learn what you want them to learn is another task, of course, we're working on. There's a lot more than the hardware that has to go into this. There has to be a whole way of working with these to do that. But some of the earliest kinds of applications we're exploring, as you might expect, are all around signal processing. So what could such a system do? If we, you know, imagine. These are some of the things we've imagined. I think you guys can imagine your own, and maybe you'll have some really nice ideas for where we can go in the future. But you could imagine eyeglasses for the blind that can take in not just visual cues, but auditory, contextual, whatever other signals that you're getting, get a large number of signals together and help a blind person navigate, you know, maybe literally through a minefield, right? So really to help them get around in ways that haven't haven't been done before. Maybe you could throw a leaf with a true north set of chips in it, a synapse system in it, into a forest fire so that it could give you information coming from all sorts of sources: video, heat, sensors, smoke detectors, sense of smell, interpretation of the feel of the terrain and how much moisture is in the area. Put all of that together and give you a much more accurate picture of where the fire is and how it might be likely to spread. How about a floating jellyfish? That's that middle one there. Something that you